Hello, welcome back to Mrs. O'Graham's Maths. This video is taking you through a parallel paper for the Level 3 Integration External. So this is a Level 3 NCEA standards-based assessment. And this is a paper, this is not a real past paper, it's one that was written to be parallel to those papers. So the first question asks us to integrate. We raise the power by 1. We divide by the new power like so. Remembering that 1 over x is the same as 2x to the minus 1. So if we raised that power by 1, it would go to 0. So you've got to use your knowledge of natural logs. 1 over x will integrate to the natural log of x, but this time we've got 2 of them. For part B, we've got the velocity, then we've got some information about displacement, time, and so forth. So this is kinematics. I'm going to start by rewriting this as 0.5 t to the quarter. We will get displacement by integrating that function, so raise it by 1. Now 0.5, let's just go over to the calculator here. 0.5 divided by that new power, which is 5 over 4, is 0.4. So that'll be a 0.4 there. And then, of course, plus c. Now, we've been told another bit of information. The object has displacement of 1 centimetre when t is 0. So s of 0 would be 0.4 times 0 to the 5 over 4 plus c will be equal to 1. So from there we can work out c must be 1. So then the displacement at 16 when t is 16, 0.4. 16 to the 5 over 4 plus 1 is equal to 13.8, and we're measuring in centimetres. Okay, for part C, we first of all need to separate out this fraction. So integrate between 3 and 5, x minus 2 on the bottom, put an x minus 2 on the top. We'll need a 3 to create the 3x. That would make 3x minus 6. We only want it to be minus 2, so we need to add another 4 to make it equal to the first thing that we had. So that's then the integral between 3 and 5 of 3, because the x minus 2 would cancel with the x minus 2 on the bottom, plus 4 over x minus 2, separating that fraction, doing a bit of algebraic juggling. If you're not confident with algebraic juggling, I do have a couple of videos you can look up on those. Okay, so if we're integrating, we're going to have 3x plus 4 natural log x minus 2 on this one between 3 and 5. So we get this next line by substituting in the 5 and then substituting the 3 and subtracting them. Now the natural log of 1 over here is equal to 0, so we will end up with 15 minus 9, so that'll be 6 plus 4 ln 3. You can leave it like that, but if you were to change that into a decimal, it would be 10.39. Okay, for D, we have the graph below. Find the shaded area. So first of all, we need these intersection points. I'm going to use my graphics calculator to get that for me. So we've got the line of x plus 2 over x, and y equals 3 is that straight line across. Now let's use gsolve, find the intersection points just here. So we've got x equals 1 and x equals 2 just by stepping through the intersections. And you can change your view window to see that more clearly as well. Okay, so we need to integrate between 1 and 2. of x plus 2 over x. So that'll give us x squared over 2 plus 2 natural log of x. Well, the 2 squared over 2 is just 2. 2 log 2 minus a half plus 2 log 1. 2 log 1 is 0, so this will be 1.5 plus 2 log 2, but that gives us the area that's underneath the curve here. So what we actually need to do is subtract it from this rectangle. Okay, so the area, or rather the shaded area, will be, well, this rectangle is 3 high and 1 wide, so it'll be 3 minus 1.5 plus 2 natural log of 2, which is 1.5 minus 2 ln 2, or if you're going to write it as a decimal, 0.1137. Okay, now for the excellence question. We've got this differential equation and some information about it. First thing we need to do is separate the variables. So we need all the y things on the left, so I'm going to bring up the y that's on the right over to the left hand side by multiplying by y. I'm going to leave the dy there. Sec squared 2x can stay where it is. The tan 2x we need to take to the other side, which means we're going to divide it. And the dx we bring over to the right hand side, and then we will integrate both sides. So if we integrate y, we get y squared over 2. On the right hand side, you need to recognize that this top bit is to do with the derivative of the bottom bit. If we differentiate tan 2x, we will get 2 sec squared 2x. So if we take a look at what that top is, it's almost the same as the derivative of the bottom, but it's twice as big. So we need to start off half as big as the natural log of tan 2x, because if the top is the derivative of the bottom, then the integral will be the natural log of the bottom. But in this case, it's half as big as that. And you can just do a quick mental check that if you tried to differentiate that, you would end up with sec squared 2x over tan x. Then we have the plus c. We've got the information given up here that we're going to use next. So when y is 2, we get this substitution here. Now tan of pi by 4 is equal to 1. Natural log of 1 is 0, so we end up with c being 2. Last, we need to find out when x is pi by 6 from the question up here. So when x is pi by 6, y squared over 2 equals half natural log of tan times 2 pi by 6, which is pi by 3, plus 2. So that comes to 2.27. We times it by 2 and then square root it. We get y is 2.133. Actually, let me just do plus or minus 2.133 because we've square rooted. Okay, on to question 2. Integrating this, pi is just a constant, so that becomes pi x. This was 2x to the minus 3, so if we increase that power by 1, we are going to have to the minus 2. We divide minus 2 by the new power of minus 2, and we just get a plus 1. Simpson's rule on part B. It's on the formula sheet. So we have a third times h, which is this gap here. So that's 0.5. We multiply that by the y things. So 1.6 plus 2 plus 4 times the odd ones in between. So 3.4, 5.8 and 5, and 2 times the even ones. That comes to 13.93. I would recommend doing that in stages and not trying to type the whole thing into your calculator at once. For part C, we are integrating between 1 and k for 42, 7x to the minus 3 to the power of a half, or 7x minus 3 to the power of half. Okay, so this is reverse chain rule. We start by increasing that power by 1, so that'll be 3 over 2. We divide by the new power, so 42 divided by 3 over 2. But we also need to divide through by the derivative of the inside, the 7. So we're going to end up with a 4 here. And again, do a little mental check that differentiates what you were expecting it to be. So if we integrate between 1 and k, that will give us 4. I'm going to actually just take 4 out of the whole lot. So it'd be, because you can rewrite that like this. So we would do 7k minus 3 to the 3 over 2. Take away 7 minus 3 to the 3 over 2. And we know that it's equal to 468. Okay, so 7k minus 3, 3 over 2. This bit just here becomes 8. Let's do 468 divided by 4. It's 117. So then if we do 117 plus the 8, and then do it to the root 3 over 2. So I'm just going to use this root function here. Then that is equal to 25. So k will be, add on the 3, divide by the 7, 4. Okay, part D. dy by dx is this thing. Work out what y is when x is pi. Okay, so integrating first of all. This is going to need separating variables again. So we get this happening, taking all of the x things to one side and the y things to the other. Integrate both sides. So 1 over root y is the same as y to the minus a half. If we integrate that, we get y to the half divided by the new power, so that's 2. If we integrate sine, we get negative cos, and then divide through by the 3. Okay, so when y is 4, so 2 times 4 to the power of a half, x will be 6. Oh, sorry, pi by 6. So 3 pi by 6 is pi by 2. Right, cos of pi by 2 is 0, so c equals 4. And we're doing when x is pi. We've got 2y to the half equals negative 1/3 cos of 3 pi plus 4. Okay, so cos of 3 pi times by negative 1/3. Well, just make it into the negative. Okay, so then add on the 4, divide it by 2, and square it. And just in case you had that as a decimal, oh, it's not going to let me do it now. 144, here we go, 1.1736, but you should be doing that as a fraction wherever possible. Okay, the excellence question on part 2. Okay, so we've got this function, find the exact value of the shaded area. So we need to do these two areas separately, so area A and area B. Okay. First, we need to know where it crosses the axis. Probably easiest, I mean, you could set that equation equal to 0, but we could also just use our graphics calculator Just delete that from earlier. Okay, so x plus 3 root x minus 4. And let's find the root. So that happens at, we've got that value just there. Ooh. So down at the bottom left hand corner we've got x is 1. Okay, so from 0 to 1, so we're going to find out that area first. So it'll be x squared over 2. 3 root x is the same as 3x to the half. So if we increase that power by 1, we'll get 3 over 2. 3 divided by 3 over 2 is then 2. So it'll be plus 2 minus 4x. And we'll do that between 0 and 1. So that's a half plus 2 minus 4, and putting in zeros, of course, would just be 0. That comes to minus 1.5. Now it's a minus because it's below the x-axis. So area A is 1.5. For B, we'll do the same thing, but oops, instead of 0 to 1, we will do 1 to 3. Okay, so if we pop the 3 in, and then the 1, I realised I made a mistake just here. That's not a 9 goes in there, it's a 3. Okay, so that altogether will come to 4.39. So then the total, when we add on the 1.5 from A, we've got the total area is equal to 5.892. Right, question 3, integrating sec 3x tan 3x. You'll find this one on your formula sheet. Sec tan integrates to sec, so it'll be sec 3x and then divide by the 3. For part B, we need to first find y. So if we integrate cos of 4x, we get sine of 4x divided by 4 plus c. So y is 1 when x is pi by 8. So pi by 4, timesing that by 4 would give us pi by 2. And sine of pi divided by 2 is 1. So c would be equal to 1 minus a quarter, so 3/4. So then when x is pi by 16, that'll be 1/4 sine of, well, 4 times pi by 16 will be pi by 4. Take away 3/4, oh no, not take away, add on the 3/4, that is c. So we've got 0.25 sine of pi divided by 4 at 0.75. Okie doke, part C. Looks like we've got some differential equations going on. So if we integrate dv by dt, we'll get v. So this will be t squared over 2. E to the 0.1t and then divided by 0.1, so that'll be 10 here, and then plus c. We've got some information when t is 0, the velocity was 15, so 15 is equal to 0 plus 10 e to 0.1t plus c. And that t can also be a 0 there, so e to the 0 is just 1, so therefore that's just 10, so therefore c is equal to 5. So the velocity when t is 15 that comes to 162.3, and we are measuring in meters per second. Okay, radioactive decay for part D. So dN by dt is equal to Kn. We need to separate variables. So taking the n to the left-hand side, so that'll be 1 over n. Then we'll get k left here on the right with the dt coming over, integrate both sides. So we get natural log of n is equal to kt plus c. N equals e to the kt plus c, which we will change into this, and e to the c is just a constant a, so in fact it becomes a e to the kt. Now the initial amount we would start with would happen when t is 0, so n equals a e to the k0. Well, e to the 0 would just be 1, so the a is our initial amount. Okay, so then we have a half-life of 5 days up here. So our amount when t is 5, we would have 0.5 of that initial amount. And that would be equal to a e to the k times 5. So that means we have 0.5 is equal to e to the 5k. Natural log of 0.5 is equal to 5k, so k is equal to a fifth natural log of 0.5. Right, back up to the question. How long would it take for 90% of it to decay? 90% means we have 10% left, so we would get a 0.1a amount. And we're trying to work out t for when that happens. So a e to the kt, but we've just worked out what k is, so that's 1/5 natural log 0.5 times t. Okay, so cancel that through. Natural log of 0.1 will then be 1/5 natural log of 0.5 times t. So t would be, if we do that rearranging here, divide it by 0.2 natural log of 0.5, and that is measured in days. Right, last one. We've got these two curves. We want to find the shaded area. Okay, so we need the intersection points. We can see it intersects at 0. We need this intersection point up here too. So I'm going to use the graphics calculator again. And actually, I did the graphics calculator. I didn't like it because it was a decimal, so I'm going to do this by hand. So if we divide through by sine x, we've got, or rather take out a factor of sine x, we can have sine x, sine cubed x minus sine x equals 0. Take out a factor of sine x, and we have sine squared x minus 1 is 0. So either sine x is 0, which is what gives us our first intersection point there, or sine squared x is 1. So sine x is plus or minus 1. And we're going to be looking for the first possible solution because it's our first intersection point between those two curves. So that'll be when sine x is equal to 1. We know that that happens at pi by 2. So then we're integrating between 0 and pi by 2 of the top function sine x, take away the bottom function sine cubed x. Now this takes a little bit of manipulating into something we can make sense of and integrate. So this will be the integral from 0 to pi by 2. Sine x is fine, we can integrate that, but the sine cubed is tricky. That's the same as sine squared x sine x dx. Now sine squared we can turn into 1 minus cos squared. And if we carry on working through this, we would get minus sine x plus cos squared x sine x. Okay, so the sine x cancels. We're just integrating cos squared x sine x. Now that is to do with the chain rule. Just over to the side here, I'm going to think about if we just started thinking about cos x. If we had that cubed and we tried to differentiate it, we would do 3 cos x squared times by the derivative of the inside. And it would end up as a negative actually. Okay, so if we go back to what we started with there, if we start that as a negative third, then it will take care of that minus 3 there. So that now is our integral. So our integral is 1/3 or negative 1/3 cos cubed x between 0 and pi by 2. Substituting in looks like this. Now cos of pi by 2 is 0, so that first bracket's gone. And then cos of 0 is 1, so we just end up with a third. And well done if you made it through that one. That was quite a tricky one that takes quite a lot of thinking outside of the box to do that one.